Welcome back to the VeraGrid Feature Spotlight series. In each episode, we explore a core capability of VeraGrid, our open source platform for modern power system analysis. Today we focus on one of the most fundamental tasks in grid studies, solving the power flow. Over the years, power flow solvers have evolved from simpler linear approximations used in quick planning studies to advanced nonlinear formulations capable of handling the most challenging grid conditions. In this episode, we'll see how VeraGrid brings all of these methods together in one place. To illustrate this functionality, we will use the IEEE 14 bus system as our base case. This widely known benchmark network is simple enough to understand visually, yet rich enough to show how different solvers behave and compare. If we look at how the system is structured, we can see the main elements that make up any transmission network. Buses act as the connection points where power is generated, consumed, or transferred. Transmission lines and transformers define how these buses are linked together electrically, shaping the overall topology of the grid. Once the physical structure of the grid is defined, the next step is to understand how electricity flows through it under steady-state conditions. This involves solving the power flow problem, which determines the voltage at each bus and the active and reactive power exchanged across the network. These results are essential for evaluating whether the system is operating within its limits, identifying potential bottlenecks, and planning future expansions or control actions. To track the results of each power flow solution, we add two live readouts to each bus. The top number shows the voltage magnitude in per unit, and the bottom number shows the voltage angle in degrees. These values will update dynamically as we solve the system using different methods. At the heart of power flow analysis lies a fundamental relationship between power, voltage, and the electrical properties of the network. The complex power injected at each bus, S, is given using the product of the bus voltage V and the conjugate of the current, which can be expressed using the admittance matrix Y multiplied by V. In a compact form, this can be written as the equation you see on screen. Both V and Y are complex quantities, with V commonly expressed with magnitude and angle, and Y expressed using its real and imaginary components. This nonlinear system captures how power is transferred through the grid and how voltages are established at each node based on the network's physical configuration and loading conditions. Solving this equation is the core of steady-state power system analysis. Several methods have been developed to solve the power flow problem, each with its own balance between speed, complexity, and accuracy. The linear DC power flow is the simplest formulation. It linearizes the equation by assuming voltage magnitudes remain fixed at 1 per unit and by neglecting reactive power, reducing the problem to a straightforward linear system that relates active power injections to voltage angles. Because of its simplicity and speed, this method is widely used for high-level transmission planning and market studies, where reactive effects can typically be ignored, and the main focus is on active flows and network constraints. The linearized AC power flow retains the structure of the AC equations, but linearizes them around an operating point. By accounting for variations in both voltage magnitude and angle, it captures more detail than the DC approximation while remaining computationally lightweight. This makes it especially useful in real-time applications such as SCADA-based monitoring, where both active and reactive power must be considered quickly. The fast decoupled power flow simplifies the Jacobian matrix by decoupling the active power and angle and reactive power and voltage relationships. This reduces the computational burden and accelerates convergence while still capturing most of the nonlinear characteristics of the system. It is widely used in large-scale network studies, including in operational planning and expansion scenarios, where many power flow solutions need to be computed efficiently without significant loss of accuracy. Finally, the full nonlinear power flow formulation tackles the original equations without approximation. Although computationally more demanding, it provides the most accurate results and is essential for detailed operational planning, studies involving reactive power constraints, and grid code compliance assessments where precision and model fidelity are critical. To solve the full nonlinear formulation, a range of numerical algorithms are available, each with its own characteristics and advantages. The Newton-Raphson solver linearizes the mismatch equations at each iteration and updates the voltages directly. It converges quadratically when close to the solution and is considered the standard method for most studies. The Iwamoto method builds on the Newton-Raphson by computing an optimal step at each iteration, improving stability on weak grids and reducing the risk of divergence without changing the fundamental structure of the iteration. The Powell dogleg method combines the Gauss-Newton and steepest descent approaches within a truss region framework, choosing the most effective path towards convergence. It is particularly useful when the initial guess is far from the true solution. The Levenberg-Marquardt solver adds a regularization term to the normal equations, allowing it to transition smoothly between a gradient descent and Gauss-Newton behavior. This improves convergence reliability and handles poorly scaled problems more effectively. Finally, the holomorphic embedding solver takes a non-iterative approach, expressing the solution as a power series in a complex embedding parameter and evaluating it analytically. It provides a globally convergent alternative that can solve difficult cases where traditional iterative methods struggle. This comes at the cost of some complexity, as any change to the formulation will require extensive reworking of the solver. Within VeraGrid, we have expanded the standard power flow formulation to capture a wider range of real-world phenomena. This includes the effect of tap-changing transformers, the enforcement of reactive power limits, the behavior of converters in meshed AC-DC networks, and unbalanced three-phase conditions. However, this extended formulation is not available across all methods and solver types. The linear methods and holomorphic embedding remain limited to the base functionality. Fast decoupled and Iwamoto nonlinear solvers add the ability to model remote voltage control and generator reactive limits. Finally, the other nonlinear solvers are also able to represent transformer and converter control possibilities and unbalanced power flows. Let us see now how everything we've discussed applies in practice. The first step we have is to set up the grid model. In VeraGrid, there are three main ways to do this. If you already have a network built in another software or exported in one of the standard interchange formats, you can simply drag and drop the grid file directly into the model. When you do, VeraGrid will generate an import log highlighting any of the missing or incomplete information. This log is downloadable, so you can review it carefully as you validate and debug your model. If a ready-made grid file is not available, you can build the network manually. To start, create the set of buses that make up your system. In VeraGrid, you can predefine the voltage levels for convenience. Once the buses are in place, connect them by dragging from one node to another. The connections are automatically recognized as lines, transformers, or converters based on their type. Generators and loads can be added by right-clicking on a bus and selecting Generator or Load. Once you've completed your model, you can edit the ratings of all of the elements in the network. One way to do this is to left-click on any of the elements within the model and edit the parameters directly on the left side menu. Another way to do this is to go into the database view and edit them in a more tabular format. These tables can be copied to an external database to keep track of all of the changes that are made. If you have these parameters available already in an external database, you can import them through scripting if this fits your workflow better. The third option is to define the entire network through scripting. The example on screen shows how this works. We first define all of the buses and their parameters, and then define the lines, the transformers, the generators, the loads, and then the final shunt. Scripts for building the model and the script for defining the parameters we showed previously as well as a sample database, are available to download alongside this video. For further information, you can also check the Grid Modeling tab of our documentation, which highlights how to define each element through code. When elements are defined through code, they may initially appear superimposed because they have no positions assigned. VeraGrid provides various automatic layout options, accessible from the panel on the right, that can arrange the network into a clear and usable schematic. Finally, once the network is defined, we're ready to solve the power flow. Before doing that, it's worth taking a closer look at the settings panel. Here, you can select any of the solvers we discussed earlier, set the tolerance for your simulation, set the trust radius, which controls the maximum step size the solver can take in each iteration, choose the maximum number of iterations, and also adjust the verbosity level of the logger, which determines how much information is shown during the solution. For most standard studies, a verbosity level of 0 is enough, but increasing it can be useful when debugging or trying to understand solver behavior in detail. VeraGrid provides a range of additional options to make the solution process more robust and flexible. You can enable automatic fallback to alternative solvers if the selected one fails to converge, adding an extra layer of reliability. If you already have an idea of the expected voltage profile, you can also provide initial voltage and angle guesses and use them as a starting point. This can significantly improve convergence speed and stability, especially in larger and more complex networks. There's also an option to ignore single node islands so that isolated elements do not interfere in your calculation. For more advanced analyses, you can activate the three-phased unbalanced calculations or use a distributed slack formulation, which shares the balancing power among the multiple generations instead of assigning it all to one. Enabling the Q limits enforces reactive power constraints on generators, automatically switching them from voltage control to reactive power control when they reach their limits. Other options allow you to model transformer tap changers, both in magnitude and phase, and to include remote voltage control. Finally, orthogonalizing controls helps avoid conflicts when multiple control mechanisms interact. Finally, you can account for equipment behavior more accurately by applying temperature corrections or impedance tolerances, and if you want a complete record of the solution, you can generate a detailed report summarizing the violations in the network. To run the power flow, simply click the Run Power Flow icon on the top toolbar. The first time the model compiles, the solution may take slightly longer, but subsequent runs will complete almost instantly. On the right side of the interface, you can customize how the results are displayed using different coloring schemes. VeraGrid can automatically assign them based on an initial power flow solution. The process sets the rating to a defined margin above the current flow. By default, only unrated elements are updated, but you can choose to override all ratings if necessary. Once the power flow is solved, you can explore the results in the Result tab. For the power flow, some of the key results to take a look at are the branch loading, the active and reactive power at each bus, and the voltage, module, and angle, which can be viewed both in the bus submenu, but also in the special plot, which contains both the voltage magnitude and angle information in a single graph. VeraGrid automatically generates a detailed log of the solution process. This includes the total elapsed time, the solver that was used, or multiple solvers that were used, the final error value in per unit and number of iterations required. If the report option was enabled, the log will also include warnings that flag potential issues in the network, such as generators operating outside their limits, overloaded branches, or bus voltage that fall outside acceptable ranges. These diagnostics make it much easier to identify and resolve problems early in the analysis. For example, in this specific case, we can see that the line from bus 1 to bus 2 is overloaded, and also that generator 1 is operating outside of its reactive power bounds. That wraps up this feature spotlight. If you have any questions or run into something you'd like clarified, feel free to leave a comment below. Check out our documentation or reach out to us directly on Discord. We're always happy to help. We'd also love to see what you build with VeraGrid, so don't hesitate to share your projects or results with us through the contact links in the description. And finally, if there's a feature you'd like to see added, consider contributing to the project. Your ideas and feedback play a big role in shaping the future of VeraGrid. Thanks for watching, and see you in the next video.